We are going to do some more shear and bending problem. Actually, one shear and bending problem. It'll probably take a while to go through it slowly. And then we'll talk about what we're going to do for lab one. So we're not on campus to actually use any kind of machinery or lab space. So we're going to do lab one as a simulation in SolidWorks, and I'll show you how to do that. Lab one talks about tensile tests. So it'll be a simulation of a tensile test that you would do if you were trying to figure out something material property wise about a piece of metal or whatever you might be testing. But we'll actually do that as a simulation instead of an actual go into the lab and test this piece of sample. So what I did is I went to WebWork and I looked through the optional problems and I couldn't find a problem I wanted to work there, as far as none of them had concentrated moments on them. So this is actually homework 13 problem 1, and it has a concentrated moment on it, and that's what I was looking for. Is this one's good because it has a distributed load, it has a point load, and a concentrated moment. So it has one of each of the possible load types that we'll use in drawing shear and bending diagrams for beams that are flexing. So I think we'll just work this entire problem. It asks for reactions. It does a couple of these where you've tried to figure out the equation that goes in certain sections, and then it wants maximum bending moment. Where is that? So this one will be kind of a little bit of everything that has to do with shear and bending in beams and drawing the shear. We will. This problem doesn't necessarily need you to draw the shear and bending diagram, but we will draw it. We'll use that part to kind of calculate this last part. You could actually, since we're going to have the equations from these three intervals here, we could use those equations to figure out the maximum bending moment. We're going to do the shear and bending diagram so that we have a little practice with that. So let's copy this down. Let's see. We'll get this part and all of that. We'll get all that. Let's put it in OneNote, and we'll just work this guy, and then we'll look at the simulation. We're going to do SolidWorks, so that'll be the simulation part. All right. So for some reason it didn't show up some of the little leader lines here, but that's fine. Let's label what we've got. So I've got A for mine, 5.3 meters, B, 3.1 meters, C, we'll put that over here, 3.8 meters. The other C, so capital C, 220 kilonewton meters. And the force point load is 16 kilonewtons. And the distributed load is 22,000 newtons per meter. Determine the support. Then it goes through what all we have to find. Basically, we need all the reactions. We need the equations in each of these three intervals, from 0 to A, from A to B, and from B to C. We need all those equations for shear and bending, internal bending and internal shear in the beam. And we need the maximum bending moment. That's the part that we don't actually have to draw the shear and bending diagram, but that we will, just to get practice with that. All right. So the very first thing is we need to, technically we should draw a free body diagram. That's the right thing to do. So maybe we should do that. Let's get some room here. Something like that. Let's draw it over here. We need to draw it anyway when we go to do the shear and bending diagram, so might as well draw it here. Didn't really want it to be red though. There we go. And then we're going to have at C, we have a pin. So we're going to have, well, that's not C, that's C for concentrated moment. This will be point A, we'll say. So we'll have AY technically there will be an AX available, but looking at our forces, there are none that have X components on them, so it is going to be AX is 0. So we can just kind of mark that out already. We've got our concentrated moment, 220,000 Newton meters. We've got our point load, 16 kilonewtons. We've got our distributed load, and it's 22 kilonewtons per meter. And then we've got our, the reaction at C is a roller, so or at the end, wherever, let's call that B. So that'll be BY. I'm not sure what the problem statement asks for. Well, it says reaction at left and reaction at right. Those are those AY and BY. Let's go ahead and put our units dimensions on there. So this one is 5.3 meters, 3.1 meters, and 3.8 meters. All right. So the first thing we could do is we could solve for AY and BY. In order to help us do that, let's put, let's see, we'll do it in blue, I guess. Let's lump our distributed load, 22,000 newtons per meter. 22,000 newtons per meter. Well, let's just keep it in kilonewtons, so 22 kilonewtons per meter. It is spread over 3.8 meters, so 22 times 3.8 is a total of 83.6 kilonewtons. And it's located, this is an evenly distributed load. Whenever you have a distributed load and you want to lump it into a point load for the purpose of maybe calculating a moment or some forces in the Y direction or something like that, then you put that lumped load at the centroid of the distributed load. So since our centroid is right in the middle, this is an evenly distributed load, this distance will be half of 3.8 right here. So 3.8 divided by 2 is 1.9. Now, let's do summation of moments about A. So I'm calling A as this point over here, and B is where the roller is. So we're going to do summation moments about point A equals 0. Clockwise moments are going to be positive in our equation. So right off the bat, I've got 220 kilonewton meters from the concentrated moment at A. Even if it wasn't at A, it would still be just 220 kilonewton meters. The only thing we have to figure out is it positive or negative? I set up this equation with clockwise being positive, and the arrow for that moment is clockwise, so it gets a positive sign. Don't multiply times distance. It already has meters in the unit, so you don't need to multiply by distance again. So plus 16 kilonewtons from the point load times 5.3 meters plus 83.6 kilonewtons times whatever this adds up to be, 5.3 plus 3.1 plus 1.9 is 10.3 meters. And then minus, so I'm actually going to write equals BY times 5.3 plus 3.1 plus 3.8. So BY would be multiplied times 12.2, but instead I'm going to divide the other side by 12.2 meters. And that'll let us solve for BY. Okay, so we just got to do this math. 220 plus, that looks like 166, but that's 16 times 5.3 plus 83.6 times 10.3. All of that divided by 12.2 is 95.564. I have to keep a lot more decimals than I normally would because we're going to plug this into Moodle, not Moodle, WebWork, and Web work likes lots of decimals usually. Now we can do summation of forces in the y direction equals 0. We've got AY minus 16 kilonewtons minus the total distributed load is 83.6 kilonewtons plus BY equals 0. We just found a value for BY, so we can plug that in and we'll find a value for AY. AY equals yeah, it'll be positive. Okay, 16 plus 83.6 minus BY, 95.564. So AY ends up being a really small number. Does that seem reasonable? Let's see. 4.036 kilonewtons. So AY is the one on the left-hand side, the reaction from the pin. Most all of the force is shifted over to the right-hand side where the roller is. So it does kind of seem like 4 is a reasonable number. It does seem really small, so this would be one that I'd want to recheck the work on, but we're going to check it by plugging them into here. So the left-hand side was 95.564. The right-hand side was 4.036. This one looks like we want to put our units in here, so let's type them in. And let's see if we're good. No, oh, whoa. What did I do? Oh, I might have typed something in my calculator wrong. Let's see. Or I might have written down one of these incorrectly. Let's make sure I didn't put something in here. I might have typed 166. Did I do that? No, but no, I did get 16.3 in there. Let me put it back in the calculator and see if I shear force and bending moment. Maybe I did something weird. Let's check it out. Or let's look at 4,090. Oh, I wrote them backwards. Oops. All right. So we didn't do any math wrong. We just did this wrong. Yeah. This one is BY, which would be on the right-hand side. Yeah, somebody noticed that too. All right, 95.56. For some reason, I was just, I don't know, I'll put them the other way. I had 564 kilonewtons, but that's not what I want there. I want the 4 right there. 4.036 kilonewtons. 95.564 kilonewtons. See if it likes that better. There we go. At least we didn't do our math wrong. We just put them in the wrong order on left and right. All right, so we did that. Why don't we go ahead and, oh, you can leave the message. You don't have to retract it. That's fine. Why don't we go ahead and draw our shear and bending diagram? The actual problem is not really set up for drawing shear and bending diagrams. The answer is not always to draw the shear and bending diagrams. That can be time consuming. This particular problem is not really set up for shear and bending. I'm just using it for a shear and bending diagram problem. This problem is really set up for doing the like little free body diagrams in each section so that you're developing the equation in each of those intervals, which is useful. That's how you would tell the difference. Maybe if you were on a test question, the way that these look different typically is, do you know if you need to use the shear and bending diagram, or do you need to just slice the beam and solve the equation? Let's see if we can find one that's really set up for what I'm thinking. Well, so on an exam, you're not going to have to do all of this. This is how web work deals with, you can't actually draw a picture in web work and have it graded. This is drawing the picture, all these blocks is. We're not going to do that on an exam. let's see, these are really set up for kind of trying to plug in a shear and bending diagram. Let me see. I wonder if in homework set 12 there's something that we can look at. Even that one's kind of set up for none of those. I think there were some in the optional though, so let's look through there. Maybe in here. We'll get to this. This is moment of inertia stuff. We'll get to that later. Okay, so like this problem. So see, it's showing you a specific section AA right here. That's saying the problem is asking, what is the flexural stress at point A, which is the top right here, on section AA? The two letters are just kind of the two endpoints of this line, that's imaginary line cutting through the beam. These problems like this, where they ask for a specific section or a point at a specific section, these problems are set up for doing just that, cutting the beam open on this section and doing the calculations to figure out what the bending moment is right there. So there will be some questions in your exam, at least, that are intended to be done this way. You don't have to do them this way. You could go in and draw the whole shear and bending diagram and do that process. It's just going to take longer. So if you see something like this, particularly if they even draw the little section marker, even if they don't though, they just say something like on a section 6 feet from the pin, or something like that, then that's a clue that that problem is set up better to be done by drawing the free body diagram of the beam cut open at that section. If you see something like all these other problems where see, there's one with the section like this. So determine the maximum, and it doesn't say anything about the maximum on a particular section. That one is intending for you to probably draw a shear and bending diagram, or there's something about that beam that just lets you know that the maximum bending moment is at a certain location. So those are the two kind of categories of these when we get into solving our, what method do you want to use to solve these? Just slicing the beam open at a point or drawing the whole shear and bending diagram. This particular problem is not really set up for either one because it's not asking for flexural stress. It's asking for these interval equations, which means you have to look in each little section of the beam, section A, section B, and section C, slice open each of those sections and draw the shear, well, not draw this, write the summation of moment equation and the summation of forces in the y direction equation. So this one does at the very end also ask you maximum bending moment, which we could get from these equations, but we're going to get this from a shear and bending diagram because we need practice drawing them. So that's what we're going to do next, is this part. So we're going to draw the shear and bending diagram for this setup. I think I'm going to need to zoom out a little bit so that we have a little more room here. It might get kind of small, but we just need more room underneath here to draw the stuff. So let's draw our guidelines. So we're going to have one here, and then we'll have one here. For the exam, you're not going to have to draw a shear and bending diagram. How I deal with the shear and bending diagrams, you're not going to have to draw a shear and bending diagram that the shear and bending diagram picture is the answer. You may want to draw one to do something like this, but that's not going to be the answer. How I deal with can you draw a shear and bending diagram is I give you a beam like this, and then I give the multiple choice questions are a bunch of pieces of shear and bending diagrams, and you pick the one that is the correct one. So that's how that'll work. So let's draw our little horizontal line for the shear. And remember, so this is V equals 0. Maybe we'll draw it with thicker lines so that we can see it. So It looks like we're going to go up by AY, which is 4,000 newtons, go across. The concentrated moment doesn't affect the shear, so we ignore that. Down 16, so we're down at negative 12, then go across. We go down another 83. So this is mostly negative. I could probably take, I can move this line. Let's move this line up higher because most of it's going to be negative. So we can kind of rethink where V equals 0 is going to be, except it's going to be contrary. Put V equals 0 up there. We'll just ignore that dot I drew. All right, so the first thing that happens is we go up 4,000. We'll call each of these, we probably will have to have a weird scale because it goes so negative. It goes down to like negative 95. So we'll try to make it in scale, but it won't be very much in scale. So that's fine. So this is 4.036 kilonewtons. Then it just goes across, and it goes. Let's get our calculator out so we can kind of keep our running total here. So we're at a positive 4.036. There's a 16,000 point load, 16,000 Newton point load that goes down, so minus 16 gets us down to negative 11. We'll put negative 11, I don't know, right here. It just won't be in scale. And then it goes across, and then there's a drop of another 83.6, so minus 83.6 gets us down to 95. We're just going to put that right here, even though that's not anywhere near in scale. And then BY is a positive 95.564, so we get back up there. So our shear diagram, not drawn to scale, looks something like this, where the maximum shear force is right there at the roller. And it is kind of high, so this would be one of the beams that potentially could actually fail in shear right there at the roller in this case. That's a relatively large shear load. So if the beam is not big enough, it could just snap right in half. Okay. Now what we need to do is integrate this, which means calculate the area under the curve, so it means add up all these little areas. So the first one is 4.036 high times 5.3 meters wide. So this is 21.39, and I'm rounding now, so I'm starting to get into where the shear diagram started and ended exactly at 0. The moment diagram, if I'm going to round here, it's not going to end exactly at 0. I want it to be close to 0. If it's not, then I possibly made some error somewhere. The next rectangle, 11.964 times 3.1. This guy is negative area, negative 31 point, I'm going to call it 1. And these units, if you look at them, the height of this rectangle is in kilonewtons. The width of it is in meters, so kilonewton meters, that's a moment. This one has two different things. It has a rectangle that's 11.964 by 3.8. So it has this part that's negative 45.46. And then it has, this is a place that you sometimes make a mistake, where the triangle part here is, it says the height is negative 95.564, but that's not the actual height of it. We're only talking about the height of the triangle, which is 95.564 minus 11.964. So the height here is only the 83.6. So 83.6 for the triangle's height times 3.8 for its base, divided by 2 because it's a triangle. And this area is negative 158.84. Okay, so now we need to put our little guideline for the bending moment. So it's gonna actually it's gonna be mostly positive. I'm gonna put it down here. Okay. And what makes it mostly positive is actually the concentrated moment. Actually, it's all positive. It doesn't dip below 0. But starts at 0, and then the very first thing that happens is I have a concentrated moment. We didn't have one of these before. That's why I picked this problem, is because it does have one. And it is clockwise 220,000 newtons. So the very first thing that happens is we immediately go up like a step change, just like a point load in the shear diagrams. We go up by 220 kilonewton meters. We were at 0 kilonewton meters, so plus 220. Let's see what's a reasonable. I want it to be maybe up here for 220. Yeah, 220. So we go straight up to there first. Then we actually go up higher. So plus 21.39. We actually go up to 240, so we'll call that here. Oops, don't want it to call it there. This is not a curved line here. This is a straight line, 241.39. I know that it's a straight line because the shear in that region is horizontal. So the shear in that region is constant. That means I have a constant slope in the moment diagram. Constant slopes are straight lines. Not necessarily horizontal, but they are straight. They're not curved. So I go up to here. Now I start dropping down. So I am at 241.39. The next little section is negative. So minus 31.1 gets me down to 210. We'll say it's somewhere, 210 should be below 220, huh? So there, 210.29. This one's also straight. And then I've got a total of negative 45.46, so minus 45.46. But I also have to subtract off 158.84, which gets me down to 5.99. So it gets me down to 6. I'm not exactly at 0, but I'm close to 0. And I don't, I did round a couple of times. I don't think I rounded by 6, though. Did I type something in? I might have typed something in incorrectly. I'm trying to look at my numbers. Everything looks okay, but being off by 6 is a little bit much, but I'm not sure where that might have come from. It could be that I rounded the reactions, I rounded the areas, and maybe all of that rounding compounded enough to where the scale of these numbers means being off by 6. That's only like 2%, 2 or 3%, so of the total maximum moment. So, the problem is WebWorks maximum tolerance is usually like 1%. So WebWork may not like this. All right, let's go down here. And this one is curved because it is a combination of this rectangle and the triangle. So the triangle is starting out with a negative, or it is a negative slope. The whole thing's negative, but it's getting more and more negative. Like the actual numbers in the shear go from negative 11 to negative 95. So it gets more and more negative. So that means that the slope of this section gets steeper and steeper and negative as we go. So it's going to start out not horizontal. It doesn't start at 0. So it's going to start out with some negative slope and then just get steeper and steeper and steeper until we get down to 0. So this is our bending moment in this beam. And it looks like our maximum is the 241.39. Here's our peak right here. And it's right underneath that 16 kilonewton point load, so at 5.3 meters. So I'm pretty sure we can get the 5.3 part right. We may not get this part right. So what number did we have? We had 241.39. Let's see. Hey, I like both of those. So that's good. All right. Got all this middle part. This middle part is the equations that describe each of these curves here. So we can see the equation. We can actually use our shear and bending diagram here a little bit. So for the first region, the shear force is just 4.036, right? So the shear in that is just 4.036 kilonewtons. Second region, negative 11.964. It doesn't change. Oh, 964? Yeah. The shear in this one does change, so we actually would either need to go and figure out the equation of this line, or we'll do a couple of these the regular way here in a second, but that should give us a couple more corrects. Oh, doesn't look like a number. Oh, does it want? Oh, I didn't put the units on it. There we go. So we got those right. Let's do one of the, the right way to do these, just so that we can develop the equation. So what you would do is, let's go back to a little bit larger here. You would take, for instance, this first section, and you would draw, cut it open right there in the middle. Draw that free body diagram. It doesn't matter if you draw the left-hand side or the right-hand side, except that the direction of the shear force and bending moment arrows are different on the left and right. So here's our little section. We know that there is a reaction at A, 4.036 kilonewtons. There's also this concentrated moment, 220 kilonewton meters. There's a shear force. That's what we just actually solved for. Well, we didn't solve for, but that shear force, this V, is, this section right here, where the shear force is just a constant 4.036. So we actually already know that. And then there's that internal bending moment. This bending moment is this thing. The equation of that line will be what we solve for when we write this equation we're about to write. So let's take this. Oh, nope, not that. I don't want that part though. There. We might have left out a piece or two. Put it down here just so we can write around it. There we go. And also we have our x-axis. All right, so we don't really need to write the summation of forces in y to get the fact that V equals 4.036, but that would be how we would calculate that one. Let's write the summation of moments, and we're going to do them about our cut surface here, the little jagged edge, equals 0. We're going to do clockwise moments as being positive. So that would say we've got 220 kilonewton meters. That's the concentrated moment, and it's clockwise, so it's just plus, minus M, plus 4.036 kilonewtons times x, whatever the variable x equals 0. The shear force on the cut surface does not create a moment about the cut surface. So we can move M to the other side of the equal sign, and we end up with M equals 4.036 times x. I don't know how they want us to do the units here, but times x with units of kilonewton meters, plus 220 kilonewton meters. And you can see that this part is just y equals mx plus b. That's the equation of the line right here. And b is the y-intercept. That's what moves us up to 220. So we need to just put this equation. Oh, I'll answer that question in a second here. Let me finish this and then I'll talk about how I got to the 241. So this equation will hopefully be liked right here. So what is it? 4.036 times x. I'm going to use parentheses. I never really know how WebWork wants this to happen, but we'll do it this way. I don't know. Plus 220. We'll see if it likes that. It did not. It doesn't want kilonewton, so it doesn't want to multiply. I wonder how it. Well, let's look at the how it puts the units in there. Let's see. It just kilonewton meters, so it doesn't do the multiplied. Maybe it just does that. Doesn't like that either. Maybe it just wants that at the very end. Like that. So you got the 4.036 times x plus 220 kilonewton meters. Maybe it wants. So this part's the aggravating part, right? Of trying to figure out how does it want this stuff plugged in to satisfy. I mean, oh, wait a second. Am I plugging it in the wrong? Oh. This isn't an interval. This only wants the, this wants us to plug 4.4 meters in for x. So it wants us to do that. I misread the problem. There we go. All right, so sometimes they want you to write an equation in for that entire interval. Other times they want you to put a number in for that exact, so they picked out 4.4 meters. All right, so the question was, how do you go from 220 to 241? So that's talking about right here. 220 is, first of all, how did we get to 220? So you start at 0. So we might need to zoom out a little bit to get all this. So you start at 0. Let's, I don't know, do this. Start down here at 0, and then we went up 220 because of the concentrated moment right here. So we were at 220. That's how we got to 220. And then to get from 220 to 241.39 is, so most of the bending moment, internal bending moment, is calculated by integrating the shear diagram. And you can kind of pick up on that looking at this free body diagram. If it wouldn't, actually, let's look at where I wrote the equation. You can kind of pick up on that here, where the moment is calculated by 4.036, which is the reaction, but it's also, whoops, didn't want to erase it, is also the internal shear force in that section of the beam. So that shear force, as we make different slices here, is creating this bending moment. So if you were to integrate that, you would end up with this area under the shear force curve, which describes the changes in the bending moment diagram. So how I integrated it was I actually took my shear diagram, it's just rectangles and triangles, and I calculated the area of each one of these rectangles and triangles in the shear diagram. That's what these red numbers are. So there's the 21.39 is the area of this first section of shear. So it's 4.036 times 5.3 equals 21.39. Then this change from 220 to 241.39 is 220, because I started at 220, and then actually I started at 0 and immediately went to 220, and then I add all of this shear the effect of all this shear force. And so the effect of that is 21.39. So 220 ends up being, or 241 ends up being 220 plus 21.39, where the 21.39 is, oh, it's kind of acting weird. That is the 21.39, which gets to the 241.39. How I got from 241.39 down to 210 is this 210 is equal to 241.39 minus the 31.1 here, or I guess plus a negative 31.1 if you want to do it that way. That might make more sense. And so that's how you progress through the bending moment diagram. Is you start at 0, and then you create change by however much your shear, the area under each little section of your shear diagram. So your shear diagram is going to look like rectangles. Sometimes there'll be triangles. I guess there could be other shapes. In this course, we're only going to deal with stuff that creates rectangles and triangles. The triangles are going to be under distributed loads because the distributed load is gradually increasing the shear, whereas these point loads, they instantly have a step change in the shear, and so that just makes it look like rectangles everywhere. The triangles end up from the distributed loads. So hopefully that helps. The easy explanation answer is that you just add on the area for that interval of shear, and that's how you get from point to point in your moment diagram. The thing to not forget is that you might have, and that's why I picked this problem out, is you might have some concentrated moments that you need to make sure that they get interspersed in there. This one just happened to be at the very end of the beam, but they could be anywhere in the beam. You could have one somewhere over here, which is going to make your point load, or your it's going to act like a point load, but in your moment diagram. So that one would be counterclockwise, so I would actually go straight down in my moment diagram. So none of that's actually true. I don't want to leave that on there because we didn't do that. It won't let me erase them. All right. So you'll have a couple of these on the exam. There are, plenty of these on homework to do. And it does take some practice. On the exam, you won't really have to draw a whole shear and bending diagram because it takes a decent amount of time to actually work through drawing the whole picture. So the exam problems are more set up for the style where you slice the beam at a specific location and do more like what we did at the bottom of the page here. All right. Let's see. I think I don't want to do any more of this part of the problem. The rest of it is just plugging in 5.8 meters. Like you could, theoretically, go to your picture here and figure out where 5.8 is going to be right over here somewhere, and you could figure out what that is. WebWork will never be okay with you just reading it off a chart. WebWork's going to have an equation like this, and you plug in an actual value for X to get it to come out right for WebWork. Plus, we didn't draw this to scale anyway, so our reading it off the chart wouldn't work very well. All right. The other part of what I wanted to do today is not beams at all. This is actually going back to the first third of the quarter where we did axial forces. So what we would do if we were in person is we would go down to a Tenius-Olson machine. Let me see if I can find a picture of a Tenius-Olson HKS. I can't ever remember the name of this thing. Well, let's just do HKS. H5KS, that's what it is. So we'd go down to a machine kind of like this one. Actually, it looks a lot more like that one. Without that, no, this is this kind of screen it had. This one right here looks like a good representation. So that little picture, maybe we can make it bigger. Nope, all the pictures are small. So we'd go down to one of these machines and we would cut out, laser cut or plasma cut, depending on what material we're talking about. We'd cut out a dog bone specimen. So something like this shape. This is the ASTM 698 or 638 shape size. So ASTM is the standards organization for testing of materials. And so they produce volumes and volumes of documents on how you go about doing a particular test. So if everybody does the test the same way, then we can compare results. So one of the tests is a tensile test, and you need to make the same type of tensile test specimen so that the test that I do can be compared to the test that you do, and can be compared to the test that somebody in some other part of the world does. And so this is a diagram of what a dog bone test specimen would look like for a flat stock material. So we would do this. We would cut this shape out of whatever material we would want to use for our project. So maybe if we're building a little wooden truss, we have some laser cut plywood or laser cut hardboard, and we want to know something about that material's properties so that we could predict how our truss is going to behave in the real world. So we'd have to do something like this to figure out what material properties, what's its ultimate strength. It probably doesn't have a yield strength because it's wood, and wood doesn't yield as much as it just breaks. But we need to know all that kind of stuff. So you build one of these. I am not going to build this exactly. What you need to do for your Lab 1 assignment is you need to follow this. I linked to this in Moodle. So if we go to Moodle, ASTM dog bone shape takes you to this page. To actually get the standards, the ASTM standards are not cheap. It's for the whole standard, not just the picture here, but the standard of all the procedure you need to do if you're running the test is probably $60 or something like that, just for that one standard. So we're just going to take the shape and draw the shape out in SolidWorks. I'm going to draw something that kind of looks like this. You can draw an actual thing that does this dimension. Now this is probably because we don't have the actual standard. This one doesn't tell us what radius to use over here, although I guess it does imply it, doesn't it? Sort of. It sort of implies this radius based on the length of these different things. So we could kind of figure out this radius right here. I'm just going to draw something that kind of looks close. So the idea is that there's this gauge width or this gauge length. Both of these are the narrow, smallest part of our little specimen, so that when we clamp it into our machine, so it's going to go between these two clamps over here, so that when it goes in there, there's our little clamps over there. Clamping it down will probably influence that little section of material, so we don't want it to break where we've clamped it. So we make the clamping areas larger so that they have more area. They're probably not going to break there. And as long as our little specimen breaks somewhere in this gauge region, then we've got a successful test. If it breaks somewhere else, then we got to figure out why it's not breaking in the gauge region, because the gauge region is the smallest region, and something has gone wrong with your test if it's breaking outside of that gauge region. Then you need to track down what that is before you go take a bunch of more samples. We're going to do all this virtually in SolidWorks. Now, there is a set of, let's see, Lab 1 summer instructions. They link to a video where I do this one way. I'm going to do it a little bit different way in this one today. So you can use either method you want. It doesn't really matter. It does need SolidWorks or something like SolidWorks. I'm going to show you how to do it in SolidWorks. You can either get SolidWorks installed from school, or you can use the virtual machine where you can log in and it just kind of runs SolidWorks in the cloud. That way you don't have to have it installed on your computer at all. You can just use the virtual machine. So I've got SolidWorks here. We're going to make a new part. It's loaded. It's going to be kind of slow because I've got streaming stuff going, and you know it's already pretty memory intensive, so it's probably going to be a little bit slow. But we'll try it out. So here I'm just going to sketch out, just for me, I'm just going to sketch out something that looks like this. I'm not going to worry that it's exactly like this for my example. Let's find SolidWorks though. Where'd it go? There it is. So first let's draw us a middle point line. Oh, also my SolidWorks does some weird redraw stuff. Just because it kind of struggling. All right, that's going to be our construction line center mark type of thing. All right, now off of this, let's build. We actually have like quadrant symmetry here, but I'm just going to use half symmetry. So we'll be able to line out here. See, this redraw makes it kind of hard to see what's going on. We'll just put an angle over here. And we'll put some dimensions that kind of keep it right. All right, so let's dimension this guy up. So let's say that from here to here is 80 millimeters. And what's our, I'm going to get close to this thing. So gauge width is 13 and the outer part is 19. Okay. So this needs to be 13 millimeters. These units are showing up in inches because I have it defaulting to inches, but I'm typing in millimeters. And let's try to get this guy. I can't remember what I think I made that. No, I didn't make it. What did I make it? Trying to think of. I don't remember what I made the thing there. That looks right though. Okay. Maybe I should change these over to millimeters, just because it's making it. Can't remember what I wrote. There we go, 13. Oh, let's make that an even number so that I can more easily get this thing centered up. So that'll work. We won't worry. This should be a little bit of a curve here. We'll put a fillet on these corners just to have one. So we'll put one there and there. Let's make it a little bit larger. Okay. So it's a little smoother. You normally don't want sharp transitions when you're going to be pulling on something. Let's mirror this. Entities, we want that to be mirrored, and we want to mirror about our little construction line there. Oh, I don't want our construction line mirrored. Mirror about that. There we go. All right, so there's our little thing. It's got all kinds of constraints drawn on it, but it'll be all right once we get it. Once we get this guy to recognize that we're done with it. Oh, we need to get this out of the middle so that we can actually extrude it the way I want to. All right, so let's trim. There we go. Okay. All right. Let's take our sketch, extrude it. How far did it say? 3 millimeters, 3.2 millimeters. We're just going to do 3 millimeters. Will be fine for what we're doing. Oh, why not do 3.2? Why not? There we go. All right, so we're going to go through and build our test specimen. So that looks good. Let's save it so that we don't have to recreate it if we mess up something. That's fine. This will be Tensile Test. All right. Now, this is where you can do two different things. So the video that's linked in the Moodle, where is that? Not WebWork. Let's close that. The video that's linked inside these lab instructions, they tell you to do a static analysis, which is fine. And you can do it that way, but it's a little better if you can. I'm trying to close out some stuff here to save some memory to make this maybe run a little bit better. If you can do a transient, so like actually watch this thing stretch. So what that's going to mean is that over here in simulation, unless you've set it up before, it's going to be set on SOLIDWORKS Premium. That sounds great, but the SOLIDWORKS Premium lets you only do static simulations, static finite element analysis. We want to do I want to do a transient one. So we're going to have to click on tell it that I want to do SOLIDWORKS Simulation Premium, not just SOLIDWORKS Premium. Otherwise, I won't have those options available. So what it's doing now in the background is loading up the SOLIDWORKS Simulation add-in. So here's my tab for it once it wakes up. And I've got New Study. So had I only clicked on Simulation tab and not told it I want the Simulation Premium, I wouldn't have any of these options. These buttons would be here, but they would not be available. They would be grayed out. I would only have static available. So if you get to here and you only have static simulation available, it means that you didn't select the premium version or the simulation premium version. And you need to go back to this add-ins tab and click on the little simulation premium option. All right, let's do nonlinear. I think that's what I want to do. I might have to rethink how to do this in a minute, but we'll see if this works. All right, so I don't know if you've done a simulation, a finite element simulation before. If you haven't done any, then it might be simpler to just do the straight static one. You don't have to worry about time steps and all this nonlinear stuff, and you can get the assignment done with just the static one. But if you're interested in how to do the next level, then this would be the next level, because what you would really do, if you had this piece cut out of some kind of material, then you would go put that in the machine. The machine would pull it apart until it fractures, and you would record data the whole time that it's being pulled apart. You would record how far is it pulling and how hard is it pulling. You would basically record those two pieces of information, and then you could plot them, and you could create like a stress-strain plot for that piece. Here, since we're doing a simulation, we're doing a simulation of the type of test that you would use to create the data that goes into this SolidWorks. So it's kind of silly that we're doing it, because the simulation is based on this test data that we're doing the simulation to get. So it's kind of a recursive thing, but it'll still show you the idea of the tensile test. So the first thing we have to do is this first part is our part. So we right click on that. It has no material associated with it right now. So I want to edit a material, because I need a particular type of material. So this is, is it steel? Is it aluminum? Is it plastic? All these different material options. And I need to pick one, and I've got to find one that'll do what I want it to do. I actually think the default one, it will work fine, but what I need is one that's going to be have this option here. I'm trying to think. I want to do the plasticity, because I want it to stretch, and von Mises. So I've got von Mises, Tresca, Drucker-Prager. I've got all these different names in here. These different names are different methods for combining our stresses. We're not doing any of this in our course. So if you go into civil or mechanical engineering, these names will mean something later on. If this is all your statics and strength of materials, then probably the one that will mean the most in the future is this von Mises one. So I want a material which this alloy steel has the option to do plasticity von Mises. So I want to click that. And I want to apply that material. So that's just this generic one. It's not even one of the, they don't all have this option. So you do have to find one that does have that option. So this one does. All right, so you can kind of tell it changed color a little bit, but over here you can tell that it assigned a material. Without a material, SOLIDWORKS doesn't have any idea of what this is. You know, it's just a math equation, really, is all it is. And SOLIDWORKS is going to do some more math on top of this math equation that looks like a picture to us, but to the computer it's just a math equation. And it's going to do some more math on that, but it needs to know what kind of response to expect, and that response is determined by the material properties. So I've done that. Fixtures. So if this were mounted in the machine, I would grab onto both of the ends and then pull it apart. So how I'm going to show that is I'm just going to fix this bottom surface. This is not how it would be grabbed in the machine. It would actually be grabbed on this face, but only only this bottom part of the face. Maybe I'll actually grab that one and that one. So this is kind of, it's kind of grabbing these faces here. It really should grab this top surface, but I'm not going to worry with that on the model. We could make it do that, but we're being pretty simple on our first go here. Now, I didn't do the other end. So what I want to do with the other end is I actually want it to move. I want it to be pulled upwards. So that's what happens in these tensile test actual experiments, is that one end stays still and the other end gets pulled upwards. You're not necessarily applying a force. Obviously you are applying a force, but you're really applying a displacement, like how far you're pulling it up. So I am going to do that on the other end. I'm not going to create that as a load. The loads here really are forces, which we could do. Don't want to do that. I don't think I want to do that. I think I want to actually, trying to think if that would work. That's probably simpler for you to do. Why don't we try it that way? It's probably simpler just to apply a force. So on this surface, but I want it to go the other way, right? The problem with applying a force is, for one thing, that's not really how the tests are done. The tests are done by applying a displacement and measuring the force. So you don't really know how much force to apply. But we'll try. I made it out of steel, and it's 3 millimeters thick, so I can probably apply a decent amount of force here. Let's put 500 pounds on it. And I've got it going the right way now. If it's pointing the other way, you click the reverse direction so that it goes the way you want it to go. I want it to pull it apart, so we'll do that. We will keep it a linear, like the force is linear. That's really not how that happens. Again, you're applying a displacement that's linear, and the force actually is non-linear, or it's having to remember our curve is not straight the whole time. But we'll try this because this is simpler to do as far as setting it up, and we'll see what happens. Let's right click on non-linear and look at our properties here. So it's set up for 1 second. Now these tests are normally 10 seconds long, maybe, because you're very slowly pulling them apart. You're not really trying to yank them apart. It's a very slow process. So I might want more than 1 second on here. But I also don't want the simulation to run very long. So let's go for 5 seconds. Just see. We will let it automatically increment the time. So it's going to pick time steps, and it's going to start out by increasing by 0.05 seconds every step, and it's got to run a new simulation, increase the time to 0.0 or 0.1, run a new simulation. But if I do automatic, then it will go in and see if it can take larger or smaller steps, time steps. We'll leave the rest of this alone. Okay. And now normally I would just hit mesh and run, but I want to create the mesh so you can actually see it. So let's create the mesh. And Again, so SolidWorks is good at letting you kind of guide you through. It even has a wizard that will help you guide through all the selections you need to make. And so it makes it look like it's not all that powerful of a solver because you've just kind of got like this slider right here. Do you want more elements or fewer elements? But there's a lot behind it that you can go in and change a lot without using these kind of easy options I'm using. So do be aware that there's more to it than what we're doing. We're kind of doing a first approximation type of thing today. So what this mesh density is how this simulation works. It's called finite element analysis, or FEA. And what it does is, the way we've been calculating stresses is, we take this thing, we chop it in half, find the internal force, divide by the area, and we know the axial stress. But in the real world, that stress that we calculated is, that's kind of like the average stress. But there's stresses that are much higher than that at different points in the object that's being stressed. And how finite element deals with that is that instead of looking at this as one piece, one tensile test specimen, it divides it into thousands of finite individual elements. And so it will analyze each one of those elements individually and connect them together. So I've got element here, it's touching this other element B, and so that boundary between them must share something in common. And so it will figure out this. It's a big giant linear algebra type matrices that gets done in the background of the computer. So I'm just going to mesh this, and we can see, there you can see all of these little triangles. Those are, each one of those triangles, it's actually a tetrahedron, so it's actually got depth to it. That's one element. And I ended up with, let's see, how many elements did I end up with? I'm trying to figure out which one is going to show me the number of elements. I never remember which one of these buttons tells me. Oh, I don't want, yeah, here we go. Details. So I ended up with 5,500 elements. So yeah, that's on the screen. This little number, total elements, 5,545 elements. So that seems like a lot. But this computer should be able to handle 5,000 elements relatively quickly. But since we're doing a transient nonlinear thing, it has to do that over and over again for each one of our time steps from 0 to 5 seconds. That's why I don't want to do too many seconds, because it could be kind of lengthy. I don't know how long this is going to take. So we've already meshed it. Let's run. Where's run? Run this study up here at the top up here. So it'll tell us if we're missing something. You have chosen to show intermediate results while running this nonlinear simulation. For this reason, it will terminate if we close the window, basically. So it was, oops, I wanted to see that window. Did I close the window? Let me rerun the study. All right, so there we go on time step number 3, number 4. So it only did 7 time steps. That's actually kind of big. And it doesn't look like, let's look at our displacement. Doesn't look, we might need more force. Actually, you know what? It might just be that this force, let's try a larger force. But we might need to actually do what I wanted to do originally, was to apply an actual displacement. Let's make this 5,000. The problem with this could be that it will break, and then the simulation will kind of fail. But let's just try. Let's do mesh and run. Yes, don't show that again. It keeps deciding to just do 7 steps though. I'm not sure why. That'll be in our properties. That's a deformation scale of 1. Can't really see it being. All right, so let's remove this load. Yes. Yes. And let's add a fixed geometry. And what we want to actually do is add a translation. So it sounds weird that it's a fixed geometry and we actually are going to translate it, but that's how they decided to arrange this. We're going to take, let's use a flat face. Let's use this face here, there. And we are going to translate that face. And we'll leave it in millimeters. We built everything else in millimeters. Now these are different directions, so they may not always make sense on which one is which. You know, normal to face, along face direction 2, along face direction 1. We want our translation to happen normal to the face that we selected. So right now it's compressing it though, so we do need to reverse that. And we need to add, let's do 12 millimeters. That's probably plenty enough. So now we've got 12, that face is moving up by 12 millimeters. Again, this would be better to, you know, actually, let's add all of these. No, because those would be pulling outwards. Let's not add that one. Let's just add this one. Again, it would be better to do the faces on the front here, but that would be more realistic to how it's being clamped. Let's do this. All right, and let's run this guy and see what we get. It's already, you can tell it's taking longer to figure this one out versus adding the force. You can see, and we could uncheck the show intermediate results, but I actually kind of want to see these intermediate results to see if it's doing the kind of thing I want it to do. What should happen, remember when we drew the stress strain diagram, it has a straight region and then it has that curved region, and the curved region actually has a peak and then it drops off. And we said that it drops off because what we're plotting is called the engineering stress strain, where the tensile test specimen, like we have on the screen, is actually somewhere it's getting thinner. It's creating this neck, and we're not accounting for that. And that's what I want to see. I want to see, can we pick up, you know, the neck forming somewhere in here? And we should be able to. I just don't know at what point we'll pick it up. And I don't know where it look, actually right there might be it forming. Let's see. See how it's getting thinner? Yeah, there it is. It's getting thinner right there. So this would be really happening in the tensile test machine, is somewhere, you don't really know where. Hopefully it is in the gauge region somewhere. But this little neck begins to form. Now again, it's going to happen a little bit faster in the machine because it's not having to actually calculate all of this happening. It's just showing it. It's just doing it. But you can definitely see the neck is forming right there now. You can see how far it is. That dotted orange line is the original shape, and you can definitely see there's a neck forming in there. That's also why we needed to select a material that had that plasticity option, is so that it can actually do this. Otherwise, it would just calculate the stresses, and it wouldn't necessarily show this neck forming. I wonder what time step we're on. We're on time of 0.8 seconds. That's up here in the corner. I told it to go for 5 seconds. So we're, you know, technically we do have enough time left in class for this thing to get up to 5 seconds. It might actually fail, like fracture, before it gets there though. But now you can kind of get the idea. This one is more interesting. I don't think it's a particularly hard study to run for your Lab 1 report. But if you can't get this to work for some reason, or you don't have the option to do anything except a static study, then the static one is fine, and it will not show this neck like this, but it'll show the force, and the stress in the part here. Now you can really start to see the stress is developing highest here where that neck is formed because it has a smaller area, and the stress, axial stress that would be measured in this is called a tensile test, but it's an axial force, pulling this part of metal apart, and the area is smallest there, and so the stress is highest there. Force over area is how you calculate that axial stress. I don't want to click on that because I don't want to accidentally close stuff. So we're at 1.16 seconds, 1.18. So it's still it's taking 0.02 seconds time steps, and I don't know. It's getting it should neck quite a bit more though before it would break in real life. I believe our simulation, if it detects that the stress over here gets too large, it will stop the simulation because it would have like ripped it apart. It won't show it broken in half, but it will stop the simulation. I don't know how long I want to let it run though, because it can get a little boring. So now on the virtual machines, they're actually a little bit more powerful than probably what you have for a computer. Maybe not, it depends on what your computer is, but these can happen a little bit faster if you use the virtual machine. The problem with the virtual machine is that the interface is kind of slow because it's Wi-Fi, or well, it's on the internet. You can really see the neck form there. Now this one did form directly in the middle. You can actually see there's our stretching of this part that I moved. You can kind of see where the original shape was, and it's moved out some. We probably could have gotten away with a fewer seconds. For instead of 0 to 5 seconds, we could have probably done 0 to 2 or 3 seconds and gotten our results a little faster. It's already solved this thing 84 times so far. One other thing that can speed it up or slow it down is when you create that mesh. If you create a finer mesh, so that means more elements, obviously that's going to slow it down. You'll get nicer looking results, not necessarily any better results, but they'll have more resolution to them. Or if you move it to coarse, it'll be able to solve it faster, but your resolution will be a little bit lower. Running the slider all the way up to fine does not necessarily mean that that is a good solution. It just means it solved it. It took more time calculating all the elements. You could still have fundamental problems in your model that are creating an incorrect solution, even though you have as many elements as you can possibly cram into your model. That does not necessarily mean that the model itself is correct. You could have one little singularity point somewhere, like a point that somehow is by itself that's kind of dominating the whole model. You could have some weird stuff like that and think you're doing a good job. So there are some correct ways to do this. If you're interested, we teach an elective class that's nothing but finite element in SolidWorks. So we normally teach that in the spring and the summer. So that would get you, obviously you need to have SolidWorks and need to have some kind of experience with, usually it's ME 350, so the CAD modeling class, before you take the finite element class. And there's all sorts of these simulations that can be done. This is just a mechanics one. You can also do thermal simulations. You can, figure out radiation, convection, all those kind of thermal things. You can do, what else is it? You can do drop tests. You can do one I did this morning in my 3D printing class is I did a topology optimization in SolidWorks where you take a block of material and you let SolidWorks do this same kind of process on it, but now what it's trying to do is figure out how much of that material it can remove and still have the structural integrity that it needs for whatever the design calls for. So you can lightweight parts that way and things like that. So there's a lot of stuff you can do with the full SolidWorks Premium simulation version. This is kind of just the very so there we go. So it made it to a limit point here. So it is 1.77 seconds. So let's see what it did. It took 119 steps, and we could go in here, show our displacement. Well, which one do I want to? Let's do this von Mises stress one. Normally you can animate these. There we go, animate. So now it's going to go through all those 114 iterations, and we can animate it and kind of watch it happen more. It must have gotten to the point where the stress got so high here that it would have broken in real life. Normally there's a little bit more of a neck that happens, but you can kind of see the necking there. Let's speed it up a little bit. I wonder if it's also getting thinner this way. It's not a whole lot. You might, yeah, you can see how it's getting. If we zoom in, you can see it getting thinner, and then when it restarts, you'll definitely see. So it's getting thinner in this direction and in this direction, and that reduction in cross-sectional area is causing higher and higher stresses, which eventually cause it to break. So the data from this, you would be able to create a stress strain plot. You could figure out your ultimate strength. You could figure out your yield strength, all those kind of things for this material. So that's how those plots and information are created to begin with. Simulating it's a little bit weird because all of that data is being used to create the simulation. So that's a little bit weird, but I kind of just wanted you to see the types of things you can do with SolidWorks finite element analysis. And for lab 1, you'll do a similar simulation to this. You'll build your model. You can do the static or this plastic one that we did here. And you will write it's not a long report, it's like a 2-page report with some pictures in it. So all of that is on here in this PDF. So we've got some time left. I don't see any new questions over there. I don't want to do any new things. Tomorrow we will come in and we'll continue our beam flexure discussion, but now we're going to talk about how do you calculate moment of inertia. So the very first time we talked about beams, we did a flexural stress equation, and we just looked up the moment of inertia for some beams in a chart somewhere. But what if you have a beam that you made or a beam that doesn't fall into a chart? How do you figure out the moment of inertia for that? That's what we'll do tomorrow mainly. Plus we'll do another shear and bending diagram, and we'll do a flexural stress calculation, kind of the whole package thing. All right, I will see y'all tomorrow at noon.